So in this video, we're going to be talking about how you can determine our linear strain from displacement. So what I mean by linear strain is I mean epsilon x x, epsilon y y, and epsilon z z. All right, so how can we determine the strain within a rigid body or within a body with respect to um, based off its coordinates? All right, so um, so when we're talking about displacement, we're talking about the movement of a point with respect to a fixed coordinate system. What we're interested in and how we can calculate the strain is we need to know the deformation of that point. So the movement of the point with respect to another point on a rigid body. So the reason that we care about this is that we can use this system in order to determine the strain within a system. So if we can determine the strain within an engineering component, we can use that strain to then determine the stress within the component. So typically on large structures, and I believe even on smaller structures, you can measure the displacement of a engineering component, and from that displacement, if you knew what the component looked like when it was unloaded, you can determine the strain field and then determine the stress field. There's actually a pretty large field in mechanical engineering and experimental mechanics called digital image correlation, or DIC, which uses this idea in order to measure the strain within an engineering component and calculate the stress. So in order to define our strain from our displacements, we can use a simple example. So we're going to start off with our undeformed square, or a very small section on our rigid body. So this is our undeformed section. All right, and that's Q, BCD. All right, and then we have, after the system is loaded and stress is being applied, we'll have a deformed section, which we'll label Q prime, B prime, C prime, D prime. Okay, so we're going to define. We're going to say that the displacement in the x direction we'll define with the letter U. All right. All right, and then the y displacement we'll define with the letter V. All right. Now there is a W, which is the Z displacement, but we're not going to talk about it in this video. So for non-rigid bodies, U and V will be functions of their positions, x and y. All right. So if we look at from going from point Q to point Q prime, all right, the x displacement, or the displacement of point Q in the x direction, is going to be equal to some constant U. All right, in a similar fashion, the vertical displacement at point Q will be equal to a constant V here. All right. For the from point D, let me highlight it. From point D to point to D prime, the displacement in the x direction is going to be equal to a constant U plus the derivative of u, or the change in u with respect to x, times delta x, plus some higher order terms in a Fourier series. All right. All right. So we can say since delta x is very small, we can say that u of d is approximately equal to just u plus du dx delta x. Right. So we can do the same thing for the vertical displacement. So we would get v of d would be equal to v plus dv dx delta x plus 1 over 2 factorial d squared v dx squared times delta x squared plus some higher order terms. All right. Again, since delta x is very small, we can assume that this is going to be approximately equal to v plus dv dx delta x. All right, and then the last point we're going to look at is we're going to look at point B. So when we're going from point B to point B prime here. All right. So if we look at going from point B to B prime, we can calculate u of b and u of d and v of b in a similar fashion to how we calculated u of d and v of d. So u of b is just going to be equal to u plus the change in u with respect to y, delta y, and then we're going to get for v of b, it's going to be equal to v plus dv dy delta y. Right. So now that we have all of our displacements for points for b prime, q prime, and d prime, we can now define our strain. Right. So from these relationships, we know that epsilon x is equal to the change in length over the original length, which is going to be equal to the final length over the original length divided by the original length. So we can say for QD, so for point Q, or for this element, we can say that L of F is going to be equal to, or the final length of the element in the x direction would be equal to Q prime, the length from Q prime to D prime. So that is this length here. All right. All right. All right. The original, so we know that from Q prime to D prime, we can say that would be equal to delta x plus du dx delta x. All right. And then we can do it in a similar way. We can define the original length as just being equal to qd, which we can say is just going to be delta x. Okay. So if we solve for epsilon x, what we end up getting is we'll get delta x plus du dx delta x, which is our length at LF, minus our original length, which is just delta x, divided by our original length, which is delta x. So our delta x's on the top will cancel out. All right, and we're left with just du delta x times dx times delta x divided by delta x. So our delta x terms will cancel out here, and we're left with just du dx. All right. So in a similar fashion, we could say that epsilon y would be equal to q prime b prime minus qb divided by the length qb. All right, so what we end up getting is we get delta y plus dv dy delta y minus delta y. So we end up just getting dv dy. Right? So though we only had a 2D case here, you could show in a very similar fashion that the strain in the z direction would just be equal to dw dz. Right? So these three relationships here are the critical relationships between the displacement of a system, which is u, v, and w, with the strains, normal strains epsilon x, epsilon y, and epsilon z. All right. So you can use this knowledge to know if you know the displacement of any point within a rigid body due to a stress. You can use this to calculate the deformation, which you can use to calculate the strain, and then you can calculate the stress. All right. So that concludes this video on finding the linear strains from the displacement within a engineering component.